Hello, everyone. Hope you guys had a good weekend. Today we are starting a new unit, and that unit is going to be gases. I know in the previous post I said we will be starting solutions. What I decided to do instead is post a link to a resource that talks about solutions, but with only 2 weeks left of school, I want to focus on gases just because I think it's more relevant. Yeah, I think this is something you'll see more frequently or run into more frequently than you will discussions about solutions. So I posted a resource for solutions if you want to check it out. But I'm going to focus these next couple days on gases. Okay. So the first section of this unit is the kinetic molecular theory. Okay. So kinetic stands for motion, and then molecules, molecular theory. So this is basically going to be talking about the motion of gas particles and what that behavior is like. That's what this section is going to be about. Okay. So this theory has five postulates or five ideas. Okay, five main ideas that this theory discusses. Okay, and all this is about understanding how gases behave. So the first thing is that gases are in constant motion, okay? And therefore, if they're in motion, they must have kinetic energy, okay? The faster the gases move, the more kinetic energy they have, which seems perfectly logical to me, okay? And the collisions of gases on the walls of whatever container they're in is what causes the pressure, okay? So just to make that clear, I want you to think about, they mentioned a balloon. Think about a balloon. I think I've showed you a video in the past where if you put a balloon in something cold, the balloon will shrink. Why does that happen? Well, now let's continue looking at another postulate. The average, or the second idea, postulate number two, says the average kinetic energy of particles in a sample of gas is proportional to the temperature. Kelvin is another unit of temperature. Okay, it's so the kinetic energy is proportional to the temperature, meaning the higher the temperature, the higher the kinetic energy. So let's go back to the first idea. It says that the pressure exerted by a gas is dependent upon these collisions. The harder the collisions, the higher the pressure. What would give you harder collisions? Well, if the particles were moving faster, you'd get harder collisions. So that means they need to have more kinetic energy, which means they need to have an increase in temperature. Okay, so back to the balloon idea. If you make a balloon cold, it shrinks. Why does that happen? Well, that's because if you cool it down, you're slowing down the particles. If you slow down the particles, they won't be hitting the walls as hard. And if you don't hit the walls as hard, you lower the pressure. And so the balloon looks like it's deflating. Okay? So that's what happens. That's what that is. So these first two ideas state that gases are always in motion, have kinetic energy, and that pressure is related to that kinetic energy, and that amount of kinetic energy is dependent upon temperature. That's what these first two ideas talk about. Okay, now let's go to the no, this is as the second one continued. If you were to average the kinetic energy of all particles, it would be proportional to the temperature. So these are essentially saying the same thing, except this one is referring to the average. Okay, not every single gas particle is going to have the exact same kinetic energy at the exact same time. But if you average them out, it'll be related to the temperature. And what they have here is a little chart showing the speed of the particles on average with based off of the temperature. So at 0 degrees Celsius, most of the particles are in this range. Okay, at 0 degrees, most of them are going that speed. If you look, you have some that go a little faster. Okay, but most of them are here. And then if you increase that temperature to 1,000 degrees Celsius, that average moves over a little bit. So now most of them are here. Okay, and you have a better spread. Okay. And then if you look at the 2,000, the majority again, are going a little faster, but this one has the most spread out. Guys, some of them go a little faster over here, and some of them go a little slower. But on average, they're faster. That's what this is saying. Okay. And when it comes to temperature, remember there are 3 units of temperature that we look at. Okay. They messed this up a little bit, so let me fix this so that it's more easily visible what they're trying to tell you here. Okay. So this should be 373. This should be 273. And then this is 0. Okay. So what they're trying to show you is just compare the different units of temperature. So we normally work in Celsius for the most part, but Kelvin is the absolute temperature, if that makes sense. So at 0 degrees Celsius, 0 degrees Celsius is when water freezes, so the H2O freezing point, and in Kelvin, that's 273 Kelvin. And in Fahrenheit, that's 32. Okay. Water boils at 100 degrees Celsius, which would be 373 Kelvin. And in Fahrenheit, that would be 212. Okay. And then at negative 273 Celsius, okay, that would be, in Kelvin, that would be 0. So 0 degrees in Kelvin. We call that absolute 0. This is as cold as something can get. Okay. Kelvin is I call it the absolute scale just because it's the one we base everything off. If you're at 0 in Kelvin, you have 0 motion. So absolute 0 means that particles are not moving, period. Gas isn't moving, nothing's moving. Everything is frozen solid, absolutely everything. Okay, so that's what absolute 0 is. In Celsius, that would be negative 273, and in Fahrenheit, that's negative 460. Okay. The scale for Celsius and Kelvin are the same. Okay. What I mean by that is that if you increase Celsius by 1, if you convert that to Kelvin, you basically increased Kelvin by 1. The only difference between Celsius and Kelvin is that Kelvin has a 273 boost, if that makes any sense. Okay. What I mean by that is if you're at 0 degrees Celsius, I guess the easiest way to look at it is here 0 degrees Celsius, you're at 273. If you're at 100 degrees Celsius, you're at 373. We increased Celsius by 100. That means you got to increase Kelvin by 100. Only difference between these two is that Kelvin has a 273-degree boost. Okay, it's always going to be 273 higher. So if you want to convert between them, Kelvin is just Celsius plus 273. Or you can do the opposite. Celsius is a Kelvin minus 273. You can convert back and forth between them easily. Okay. Why they did that, I don't know. Okay. The history behind that stuff, I can't answer, but just know that that is the case. Okay. These slides are basically practicing temperature conversions. I'm not worried about the conversion practice, so I'm gonna skip these. Okay. Now let's go to the third postulate, or the third idea from the theory. What the third postulate states is that collisions between gases are perfectly elastic. That is a physics term. When you get to physics, you will learn about the different types of collision. There's elastic collisions and then there's inelastic collisions, okay? Inelastic collisions mean that when some things crash together, they stick together. That's an inelastic collision. Let me give you an example of that. Football. When you tackle somebody, when you tackle somebody, you run into them or you collide with them, but you don't bounce off of them. You stick together. You tackle them, you grab that person, and you take them to the ground. That's an inelastic collision. An elastic collision, you assume that you have a perfect bounce and energy is transferred 100% perfectly without any losses. An example of that would be billiards or pool, pool table. When you hit the cue ball, the white ball, you hit it and you bounce it off of the other balls to try to get them into the pockets, right? That's an elastic collision. Cue ball hits the ball, they bounce off of each other, the energy gets transferred, and the balls continue on their merry way. Okay. In elastic collisions, or specifically in perfectly elastic collisions, there is no loss of energy. So whatever energy these balls had when they crashed into each other, whatever energy they transfer, if you add up their energies, it'll be the same as before you crashed, okay? So what they're saying is the total of these two, this is before they crashed, is always going to be equal the total of these two after the crash. Okay, the total energy before is going to be equal to total energy after. Okay, so the total kinetic energy in the system is always going to remain the same. This is important because this means that gases do not break the law of conservation of energy. Okay, we always say energy cannot be created or destroyed. Okay, so energy can't appear out of thin air. However much energy is there is the energy that's there, period. Okay, so that's what this third idea is saying. Okay, when these molecules crash together, they transfer energy to each other 100% perfectly, but nothing new is gained and nothing is lost. Okay, now we have the fourth idea. Okay, the fourth idea is that particles, the gas particles, are so small compared to the distances between them. Okay, they are so tiny that the individual particles we say do not have a volume. Okay, we assume the volume of these little dots, these individual particles, are zero. And if that's the assumption we're making, that means the volume of all gases has to be the volume of the container. Okay, this postulate isn't saying that gas doesn't take up space. What it's saying is that if you were to look at an individual particle, you would assume the volume is zero because the number would be so tiny. Okay, for example, like this is just a random number, but like 1 times 10 to the negative 99, okay? This negative 99 means you have so many zeros in front of that. This would be 0.000000099 zeros until you get your 1, okay? So that's basically zero. That's what they're saying. These particles are so tiny that individually we assume they have no volume. And if that's the case, that means the total volume of the gas is going to be whatever space it's in, because gases always expand to take up as much space as possible. Okay, they're always moving around and they expand to take as much space as possible, and they always take up the volume of their container. Okay, so if we had, let's say, hydrogen gas, pure hydrogen gas, and you stuffed it in a water bottle, okay, the volume of the gas we would say is the same as the volume of the water bottle. If you were to move that same gas and instead of putting it in a water bottle, you put it inside a I don't know, what's a giant container. Instead of a water bottle, you put it inside of a pitcher. Okay, a giant pitcher. Pitcher of anything. Pitcher of water, sealed, but make sure it's sealed. The pitcher is bigger, but the gas is now going to occupy the space of the pitcher. So now it has a different volume. So because the volumes are changing, other things are changing. We're going to talk about pressure and other things in the tomorrow and other properties or characteristics of gases. But just know that gases take up whatever volume the container is in. And if you think about it, if you force something into a smaller container, obviously there's going to be more pressure. Okay, so if you force the same amount of gas into a smaller container, pressure is going to get higher. Okay, but just gases take up whatever space they're in. So gases in a room, the volume of a gas in a room is just the volume of the room. Okay, because gas is occupied to fill up as much space as possible. Okay, that's what this theory is saying. That's the fourth idea. And then the final fifth idea, you have this thing called intermolecular forces. I'm sorry. And intermolecular forces refers to the attraction and repulsion of different particles. Okay, we talked about positive and negative charges on compounds before, and as we know, opposites attract. So positive is attracted to negative, and if they're the same, they push each other away. What this is saying is that the intermolecular forces between the gases are too weak to exist. So therefore, we pretend that there are no forces of attraction or repulsion acting on the gases. Okay, so if you have a gas and you have a bunch of molecules, there is no pushing or pulling on the molecules towards each other. They're all moving randomly. Okay, that's what the first idea states. Okay, they have energy and they're in constant motion, and they're going to run into each other, but they're not going to run into each other because they're being pulled or pushed away from each other. Okay, there is no attraction. They're just randomly moving and they randomly run into each other. Okay, that's what the fifth postulate is saying. So all the point of these postulates is to just give you a foundation on the behavior of gases that we can then build upon and talk about other things. Okay, and let me give you some insight into the next one for tomorrow, where we talk about characteristics. Because of that no volume of particles behavior, gases expand to fill up their containers. Okay, so here you have a container, and here the gases are being pressed down to occupy less space. If you were to lift this pin up and give it more space, all the gases are going to do to they're just going to expand to fill up the new amount of space. If you had a liquid, there is no expanding of a liquid. Okay, if you this is water, the water is filled up to here, and then you lift it up so that there's more room. The water isn't going to magically rise, but it will in gases. Okay, you lift up the pin, the gases are going to expand because they're always moving around. Okay, it's that constant motion that causes it to expand. Okay, and because of this, you're going to reduce pressure. If you lift this pin up, you're putting less pressure on the gases. So pressure goes down, but volume goes up. Okay. P pressure goes down as volume goes up. Okay. And we'll learn about an equation that you can use to explain that eventually. Okay. But this is what I want you to get out of today. It's just the behavior of gases. Okay. This little table is what I want you to get today. Okay. So a quick little recap. The five main ideas of this theory is that number one, gases are in constant motion, and the energy of motion is kinetic energy. Therefore, if they're moving, they must have kinetic energy. That's the first idea. The second idea is that the kinetic energy of the particles is proportional to the temperature. When you see the word proportional, if something is proportional to something else, what that means is that they increase together. Okay, so as temperature increases, kinetic energy increases. That's the second idea. The third idea is that no energy, absolutely no energy is lost when the particles crash into each other. They don't lose energy because we assume that the collisions are perfectly elastic. That's the third idea. No energy is lost in collisions. The fourth idea is that individual gas particles, we assume, do not have a volume. They are too tiny. We assume their volume is zero. It makes the math simpler. If we assume that the individual particles have to have zero volume, that means that the gas of the volume is always going to be the same as the container, because something can't have zero volume. Okay, they occupy some space. We just assume that the individual particles are zero. Therefore, the volume of the gas is going to equal the volume of whatever container it's in. Okay, that's the fourth idea. And the fifth idea is that the particles do not have any attraction or repulsion to each other. There is no pushing or pulling between the molecules. Okay, there's only constant motion. Okay, and the reason that fifth idea we make that assumption is because it goes back to the first one. The gases are in constant motion. They don't have time to be pushing or pulling towards each other. They're going too fast for that to even happen. Okay, the intermolecular forces are too weak. So we just pretend that they don't exist. Okay, those are the five main ideas. Okay, for those of you that get deeper into science and maybe engineering eventually, what you'll discover is that a lot of theories have to be centered around an assumption. Okay, we make an assumption and we make predictions based off of those assumptions. You have to make an assumption because you need a foundation to work off of. So a lot of theories, okay, we are making assumptions and we're taking many shortcuts. Okay, So, for example, the one idea number 4, where we say the individual particles have zero volume, that's kind of a shortcut because technically they do have a volume, but the math behind it would be so complicated, it's not even worth it. Okay, the particles are so tiny, they don't contribute that much that you can really ignore them. Okay, it really doesn't matter. Okay, the best analogy I can make is with money. Okay, if you have $1 million and you find a penny on the floor, compare what you had before to what you gained. Percentage wise, did you really gain that much? No, you didn't. If you were broke and you found a penny, then that would be more impactful. Okay, I'm just using that reference to talk about impact. So sometimes you have to take these math shortcuts and these little shortcuts to move forward, because sometimes they're not even worth dealing with because they don't contribute that much. Okay. So that's it for the presentation for today. How are we doing on time? How are we doing on time? Okay, 20-minute mark, 21-minute mark. Okay. Today you have a 7-question multiple choice worksheet. Okay. This is just going to summarize what we talked about. Okay. This is just, this will give you a quick little recap. If you paid attention as you went through the slides, you can breeze through this quickly. Okay. This is just, it summarizes all the ideas in this presentation, or in this first section, the kinetic molecular theory. Okay. I'm not going to go through an example because there's not that many questions and it's all multiple choice. But this is what you have to do for today, just his worksheet. Okay. But that's it for today. Again, hope you guys had a good weekend. If you have any questions, as always, please feel free to reach out. But that's it for today. Okay. Take care, everyone. Be safe. Have a go.